Okay, so let's start. So I want to start with this example that I hinted on last time at the end, and then we're going to wrap up what we did before, answer some questions, and continue. So here's a machine learning puzzle. So you're given data. Here is how the data is given. Your training data is n plus 1 tuples. Let's think about everything as Boolean. So I denoted here x0 to xn. So n plus 1 tuples. Your goal is, I told you that in test, I'm going to give you x1 up to xn. So your goal is to predict the value of x0 given these assignments to n variables, given these test examples that have n variables. What would you do? Yes.
I guess condition the probability of x0 being 0 given that x1 is x1 at x2 is x2 and all the way to xn.
Okay, so that's what you want. So you're saying my prediction is based on the probability of x0 given the rest versus the probability, or the probability of x0 being 0 versus the probability of x0 being 1. So this is, say, the standard Bayesian model, but the devils is in the details. What exactly are you going to do? So that's, how would you estimate this?
Treat x0 as my response as my y. And given all my training data, I see how often x0 is 0 given a certain distribution of the other x's.
Okay, so what do you mean by how often? I mean, give me an algorithm. Do we have in our bank of algorithms from this semester ways to deal with this problem? Did we have 2 months ago ways to deal with this problem? Yeah? I can do decision tree. What do you mean by decision tree? How would I model it to use decision trees?
Find a feature that generates our highest
Map this to your terminology, map to this slide. What do you mean by feature here? What are the features?
one out of x1 to xn that can generate the label x0 being either most 0 or most.
Yeah, so all the students here know decision trees very well, so they don't need these details. You can just tell them, here's a data set. x0 is the label, x1 up to xn are the features. Run a decision tree algorithm. Yeah? You're comfortable with this level of description? I have a data set. The features are x1 up to xn. The label is x0. Run a decision tree algorithm. Is that okay? Yes, no? Who thinks yes? It's good enough definition for you to take the data and run with it. Who isn't comfortable with that? Most of you don't have a view at all. Assume that this is your homework set. Given this modeling, can you do it? Yes, no? Yes. Who thinks no? Who is not comfortable with this level of description. What's the problem?
I'm not sure how to phrase it.
If it's not binary,
Okay, but it is binary.
then yeah.
But by the way, it shouldn't bother you also if it's not binary, because the same algorithm is going to work also for categorical variables for the x1 to xn. x0, we will have to do multi-class classify. Now, why decision trees? I mean, you chose decision trees. Anyone else would have other suggestions?
You could look at the frequency, starting just with x0 and x1. On the training set, count how many occurrences you have of just those two pairs, assign proportions, and then use that as a very simple prediction. And then you could simply just begin using x2, x3, x4, and then just again count the proportions and use that as a way of prediction, just by looking at the occurrences.
Why do you think that would work? I mean, what are you doing here? It's not, give it a name of an algorithm that, or an approach we've discussed, or convince me that this approach is going to work otherwise. I'm not saying it's not going to work. I just want you to, you have tools now.
This is kind of like naive faith.
Okay. But still, okay, so what you've done is you made some conditional independence assumption, and when you said proportion and so on, what you really meant is, I want to know P of x1 given y, given x0, P of x2 given x0, and so on. I'm making the naive Bayes assumption. But still, you're comfortable with me calling this a supervised learning problem, with x0 being the y, and x1 up to xn being the features. You just chose a different algorithm. Yes?
This is just one example of the x0 xn.
Yeah, but I told you that I'm going to give you a sample of data points like this.
So you have a bunch.
I'll have 1,000 like this. That makes it easier? So it's a sample of data points like this.
And we have 1,000 labels according to those.
I haven't used the word label on purpose because some of you used it. I did not, but some of you suggested that because this is an n+1 tuple, and I told you that in the second line, predict the value of x0, it's okay to think about x0 as the label. Okay? I didn't say that it's the label. I just told you here are n+1 tuples, but it's okay to think about x0 as the label, right? I don't know what's related. When I give you data, I have no idea what's related and what's not related. The data was taken from somewhere. You took it from Kaggle for your project. Do you know that these are related? Someone put it there. So this came from some problem, but I didn't tell you which problem it came from. We can invent a story of where this came from, but that's the data. Now you have a bunch of tools. Decision tree was one of them. Can you try other algorithms on this? Give me a name of an algorithm. Why did you choose decision trees? What about SVM? Can you use SVM here? How would you use SVM? It's the same problem we solved for the last 2 months, right? It's just, I just renamed things a little bit, but it has to be clear that this is just the supervised learning problem that we talked about throughout the semester. Okay, it's clear, not clear? That's your best chance to ask a question about it. Yes?
So I just want to clarify that here, x0, like the way it's defined,
No. I mean, read what's written here. A sample of data points. Each data point is x0, x1 up to xn. This data point is a member in 0, 1 to the n plus 1. This is the meaning of this math, right? This is an n plus 1 tuple, and it's a member of 0, 1 to the n plus 1. That notation should be clear. There's no ambiguity here at all. Okay, so nevertheless, the title of this slide is this. Why? Because there's another way of thinking about it. So what would be the other way of thinking about it? So this is data. You can think about, in machine learning, we can think about the data that we see in multiple ways, as we've already seen. So one way would be, okay, someone gave us data and then added the labels on it. In this case, the data is, each data element is x1 to xn, and someone put the label. x1 to xn could be a collection, could be a document. So my data set is a collection of documents. And x0 is whether this is an interesting document or an uninteresting document. And then in test, you just given a document, and your job is to say whether I think it's interesting or not. It could be x1 to xn could be a set of images, and x0 is whether there is a cat in the image, yes or no. All the supervised learning paradigms falls into this. But I can also think about it other ways. Any suggestion to think about it in another way? Yeah?
I was just thinking, like, if you're missing a feature, like, you could create the features, not necessarily being labeled.
Okay, so you want to think about x0 is as a feature.
Yeah, just as like a missing feature.
So in some of the data, it's not missing. And in some of the data, it is missing. So I think you're getting to what I want to. So I actually was told that the way the data was generated was like this. So again, these data sets, x subscript I, each x subscript I is an n plus 1 tuple. First of all, someone he imagined a variable that I called here z. This z takes k values, 1 up to k. And it takes these values with probabilities alpha z that sum to 1. This is a hidden variable. Now, once you chose a value to this z, we choose the values xi for each observable, capital Xi, to be 1 with the probability piz and 0 otherwise. Okay? So you can think about it as this picture here. First of all, I generate a z. Let's assume for now, for a second, that z could take only 2 values, 0 or 1. If it's 0, I generate x1 up to xn, in this case x1 up to x4, with some 4 probabilities that I call pi 0. If it's 1, I generate it with probability pi 1. Okay? Is the model clear? Yes? What's alpha z is the probability to generate a specific value of z. So let's assume that z can take 2 values, 0 or 1, so it's going to be alpha 0 or alpha 1. That tells me how I determine the probability of z. So we can think about z as a coin if you want. head or tail. It's with probability alpha 1, it's head, with probability alpha 2, it's tail. The sum of them is 1. If I got head, I'm generating x1, x2, x3, x4 with probability p head, p1 head, p2 head, up to p4 head. If I got tail, I'll generate these x's with probability p1 tail, p2 tail, p3 tail, p4 tail. Okay? That's how I generated the data. Now, I didn't do anything. The data is still this. All I did is I invented the story on how this was generated. You can still run your algorithm that you ran 10 minutes ago on this data. But given that I gave you this story, you have another option now. Right? What is your other option? You can think about it now using EM. So it's the solution that you suggested. Think about this x0 as potentially a missing variable. Right? So I'm going to estimate all these parameters, the alpha z's from this picture, and the pi z's using EM. Once I have this, I can do whatever I want, right? I can compute the probability of p of x0 being 1, given x1 up to xn, and I can compute the probability of p of x0 being 0, given x1 up to xn, and I can make a prediction and choose what I like x0 to be. Right? So this is one option that I have. I'm going to call it the parametric option. Learn the model using EM. Again, what are the parameters of the model? The parameters of the model are the PIZs and the alpha Z's. Okay? I have also the non-parametric way, which is what you said before, just supervised learning. Learn x0 directly as a function of other variables. Of course, the question in each case, parametric and non-parametric, I have to ask myself as a machine learner a couple more questions. In the non-parametric, you have to decide which set of hypotheses do I use. Do I use decision trees? Do I use SVMs? Do I use perceptron with kernels? Right? So this is choosing the hypothesis space. Do I use neural networks? But it doesn't matter. It's the same non-parametric approach. I have supervised data, and then I learn a model for x0, and I predict x0 once you're giving me test data. In the non-parametric, in the parametric way, I also need to make an assumption. I need to assume a probabilistic model. We can assume the naive Bayes model and run with it. Is it clear that you can do both things? Yes, no, questions? Okay, so again, this is the picture that you want to have in mind. I kind of moved x0 above there. Now I call it z, but it shouldn't bother you. It's the same thing. Now, I also generalized it a little bit by telling you, now I'm not sure that z can take only 2 values. Maybe it can take 5 values. Again, shouldn't bother you at all, because it's going to be exactly the same algorithm. Right? In the discriminative case, it will be a multi-class classification, or what I call here the non-parametric. It will be a multi-class instead of a Boolean. And in the EM case, it will be a variable that takes more values. So instead of just estimating P of z being 1 and P of z being 0, the alphas, I'll have to estimate P of Z being 1, P of Z being 2, P of Z being 3, up to P of Z being 5. Conceptually, it's really the same problem. Okay, so why do I tell you this? Because multiple reasons. One is because you can see that the same problem, the same data that you're given, you can think about it from multiple perspectives. You can solve it using conceptually. I mean, you knew before that in the non-parametric part, you can choose SVM, perceptron, decision trees, multiple algorithms, but really they do the same thing. Now you have a completely new set of tools, the parametric ways. You imagine a probability distribution or a family of probability distribution that could have generated data, and you can learn the parameters. And as we'll see in a second, this has advantages and disadvantages. But before we get to it, first of all, it has to be clear that we don't know which one is going to work better. In fact, it's an interesting question, which one is going to work better, and I'm not going to ask you to guess because no guess is actually going to be good here. But here is one thing that is interesting here. It turns out that if it so happened that K is 2, which means Z takes 2 values only, X0 takes only 2 values, then X0 is really a linear function of the other variables. So you can just do the algebra and get it, which means that these two ways, in principle, are you can compare them, right? So you can say, okay, I'm going to run my SVM, or I'm going to run my EM. Because it's truly a linear function, so my assumption, in both cases, I'm making the right assumption. On one case, I'm assuming K equal 2. In the other case, I'm assuming it's a linear function, and I'm running a linear function. I can compare. Now it's a fair comparison, and I can ask you which one is going to work better. Which one is going to work better? The non-parameterized. Actually, in this case, the parameterized is going to work better because the assumptions are correct. Everything that I did, I really generated the data this way. I chose Z, I had 2 options. Either Z is 0 or 0, 1. And given Z, I generated each one of the xi separately, independently, so conditional independent holds. So x1 is independent of x4 given Z. Actually, it's going to work very well. EM is going to work here perfectly. It's going to learn faster than your linear functions. You choose your favorite linear function. But, so when K is known, the EM approach performs really well, actually, I should have said. EM is a very good algorithm when the data is really generated according to your assumptions. On the other hand, here is what I can do here. I can cheat my algorithm just as a game, and I can say, you know, I really generated the data from K equal 2. But I'm going to tell my EM that it was generated with K equal 5. Okay? I can do that. I can run my algorithm with K equal 5, because in real life I don't know what K is. In this case, it's not going to work as well. And vice versa, right? I can also generate the data from K equal 5 and tell it that it's K equal 2. Now notice that if I really generated the data from K equal 2, my linear function here is going to work very well. If I generated the data from K equal 5, my SVM or perceptron or logistic regression are not going to work as well because it's really not a linear function. So I can play all these games, and the bottom line of what's going to happen here is that once I generate the data based on some distribution and tell EM what is the family correctly, EM is going to beat the other algorithms. If I don't, then the linear function is going to do better. It's even going to do better when it's not a linear function. It's going to learn faster, and it's going to do better than the probabilistic method. So, okay, what is the lesson here? One lesson here is modeling. I really want you to be able to look at a problem like this and say, oh, these are the approaches that I can use. Don't be bothered by the fact that I call this x0 rather than y, and that I put the label to the left of the example rather than to the right of the example, which we used to do before. It's a machine learning problem. You have data. You should be able to think about it. And you should think about the fact that there are conceptually different families of learning algorithms, or modeling if you want, and each one of them makes somewhat different assumptions. Yes? K is the value, the number of values that Z can take.
So why would you not know how many values? Like, isn't that just what your labels could be? How would you not know?
So in the way, when I drew this picture here, so two things could happen. First of all, maybe I don't see it. Maybe I didn't see all the values. The way I presented it here, yes, I gave you x0, so you see the values. But this formulation here could also hold when I'm hiding x0, right? Remember the coin problem, the third version of the coin problem. I didn't show you x0, I just show you that. This formulation is going to work in that situation also.
But wouldn't you know that it's either going to be a head or a tail, so then it's
No, maybe it's a dice rather than a coin. So I could have generated the data many ways. So as an example, last time we talked about clustering at the end, K-clustering. K-means clustering. We're going to talk about it next week again. In this case, what you see is data. You don't know how many clusters it came from. So you don't know K in this case. You just know that for one K, one value of K, data was generated. From another value of K, data was generated somewhat differently. From a third value of K, data was generated somewhat differently. But you don't know how many Ks, and for each data point, you don't know which K generated it. So that's the picture that I have here in the top left. And that's the more realistic situation. Okay, yes?
In this example, the previous one, from the parameters of the model, we can learn like the probabilities for each individual legs, how they're going to be generated, but can we also learn what the alpha values are going to be like?
Yes, so let's go back to the coin problem that we did last time. We had a coin that we flipped. Based on this coin, we decided which of the other coins to use, right? So we had three parameters then. We had the probability of the original coin. This is like the alpha here. And we had the P and the Q, the coin 1 that had P probability for head and coin 2 that had Q probability of head. It's really the same situation. This is a little bit more general. Why? There, I first tossed my first coin, the alpha, and then I did m times with the same coin, either the P coin or the Q coin. And then I tossed the alpha again, and then I chose a coin, either the P or the Q, and tossed it m times. Here, after I chose the alpha, I have different probabilities. It's not only one P, it's P1Z, P2Z, and so on. So it's a little bit more general than just the coin, but it's really this very similar story to what I had with the coin. Okay, so yes?
Can I know what's the relationship between like the number of possible values we can take for Z and whether the data is kind of linear separable? Are these two things related?
Yes, yes. So as I say here, it turns out that if k is 2, then x0 is a linear function of the other variables. So you can write this down. I'm not going to do it, but it's not complicated to write this down. If k is equal to, you can write x0, or the decision function for whether x0 is 0 or 1, as a linear function of the other variables. And that's why it's a fair comparison, right? So for k equal 2, I can run a parametric and a non-parametric, and my assumptions are correct in both. So I can really do a fair comparison between these two algorithms. If k equals 3, it's no longer fair. Because if I run a linear function, it's unfair to the linear function because it's really not a linear function.
So you're saying that if k equals 3, the data is not going to be separable based on the...
Yes. So x0 is not a linear function of the other variable. So if I look at this data set that I showed here, this data set, 1,000 examples like this, and I'm thinking about x0 as my label, the data is not linearly separable if I generated it from 3 values. Okay, so hopefully this is clear, and I want to make one other comment on this, which is another important distinction between parametric and non-parametric. So if I took the parametric approach and I estimated all the parameters, so I have my PIZs. What are the PIZs? Again, these are the probabilities on these edges here. How many are there? Number of z's, let's say k, times n parameters, right? PIZs, plus k, which are these alpha k's. If I estimated all these parameters, I know everything about this distribution. You can now ask me other questions. I can predict more things than just x0. For example, you can ask me, let's assume that you observed, okay, so x1, x2, and xn. Right, the rest are missing here. Can you tell me what's going to be the probability of x0 being something, x7 be something, and x8 be something? I can compute it now. So we're going to do this a little bit later today, but I want to make sure that you can actually do it yourself. Right? Once you have all the parameters, you have the joint probability distribution over these n+1 variables, any event that depends on these n+1 variables, you can compute the probability of. On the other hand, if I took the non-parametric approach, I just learned my SVM, all I can do is predict x0 as a function of the others. I cannot tell you if suddenly x7 is missing, what is the probability of x7 given the other things? I have to invent a new learning problem, look at the data for it, learn a model for x7, and then I'll be able to do it, right? So that's an important distinction that in fact is a very important distinction nowadays that people claim in the newspapers that AI is solved. Because it's important to realize that neural networks, for example, or decision trees or SVM, they isolate one variable and learn a model for this variable as a function of the others. If I want to ask another question on the variables in question, I cannot do it. I don't have a model for that. On the other hand, if I've learned a probability distribution over all variables, I know everything. I can answer any query relative to the data. Now, you can think about whether you want it or not. Maybe in some cases you do, maybe in some cases you don't, but the difference has to be clear. Questions? Okay, so this is a good segue to what I'm going to talk about next, which is thinking a little bit more about probability distribution and representations in general. Before that, I want to also summarize what we did on EM. I know that many of you had questions. What I'm going to do is I'm going to make one suggestion now, and I'm going to add one more detailed examples to the notes that will be there today or tomorrow, so you can consult it. But first of all, what have we done about EM? We said that EM is a general procedure for learning in the presence of unobserved variables. We showed how to use it in order to estimate the most likely parameters, or the most likely density function, if you want, of a mixture of probability distribution. I don't know if I used this terminology before, but basically, the two examples that we gave, you can think about as a mixture. So you had a Bernoulli distribution for the P coin, you had the Bernoulli distribution for the Q coin, and I mixed them using the top coin, which was the alpha coin. What do you mean by mixed? When I showed you a data point, you knew that with some probability it came from the P coin, with some probability it came from the Q coin, but you didn't know from which. So that's what we call a mixture. Same thing with K-means. When you have K-means, you have K clusters. We assume that we know K now. And when you look at a data point, you know that it came either from the first cluster that had mu1, or from the second cluster that has mu2, or from the kth cluster that had mu k. You don't know which one. You know that these clusters were mixed with some probability. With some probability it came from mu1, with some from mu2, and so on. So this is a mixture. So that's what we've learned how to deal with. EM, as you saw, is an iterative algorithm. It can be shown, and I haven't shown that, to converge to the local maximum of the likelihood function. So basically what can be shown about EM is that every round, when you update your parameters, you improve the likelihood of the data. So the likelihood of the data under the new parameters is higher than the likelihood of the data with the old parameters. That's what can be shown. Now that means that it's going to go up, but may not be the global maximum because it could get stuck in a local maximum. And that's why this algorithm in practice requires restarts. We have to understand, to know the probability distribution that we're using in order to derive the update rules. And as I said, it's actually a very, very good algorithm. Once your assumptions are reasonably good, they don't have to be exact, the algorithm is surprisingly good. Now in practice, and I said this a little bit when we talked about K-means, and I'm going to say it again, the K-means algorithm that we gave basically assigns for each data point a probability distribution over which cluster it came from. So I don't really know which cluster it came from during the algorithm. I'm saying, well, with probability P1, it came from this cluster. With probability P2, it came from this cluster. Probability PK, it came from this cluster. So every example I think about as fractional examples. I use this term, where part of it is here, part is here, part is here, part is here. In practice, many times people don't run EM this way because it's time consuming. They just say, yeah, I'm going to choose the highest value and I'm going to place it in this cluster. That's called the hard EM or sometimes truncated EM. And in practice, many times when you read in a paper that people told you, I used EM, they actually used hard EM. And there's a lot of literature on which one is better, when, and how. The bottom line is, if you have good initialization, hard EM is going to do well. If you have poor initialization, hard EM is going to do poorly. It's going to take you in a direction that who knows what it is, you want to use the real EM. Questions on this? I want to make one more comment that maybe will incite more comments or questions. So, to me, the easiest way to think about EM is the way it's described in your extra credit in the homework. Even if you don't do the extra credit, which is going to be somewhat time consuming, read it and think about it. What does it say? It basically says the following thing. You already ran naive Bayes in experiment 1 and 2. 1, simple naive Bayes. 2, naive bets with bootstrapping. EM is essentially an extension of bootstrapping. What does it mean? It means that what are you doing in experiment 2? You train your naive Bayes on a small number of examples, let's say 10% of the data that we gave you. Now you have a model, which means you have parameters. The parameters are P of xi given y for all the xi's, and P of y, the label. You have these parameters. Now, when I give you a new data point, you can predict on it, right? So in experiment 2, that's what we ask you to do. We ask you to take your model and predict on all the other data points, choose a subset of them, doesn't matter now how, I don't know. You choose those that you are most confident about your prediction based on some definition of confidence, put them back into your supervised data and learn again, use naive Bayes again. Very simple algorithm conceptually. What is the difference? This is hard EM. What is the difference between EM and this? When you make the prediction, you look at your data point. It could be 0.8 positive, 0.2 negative. Don't make a decision and label it as positive, but rather split it and keep 0.8 of it as positive, 0.2 of it as negative. Add this to your data set. And now when you run naive Bayes, run it with the same examples, but with fractional labels. What does naive Bayes do? It basically does counting. Count fractions. That's it. That's EM. And keep on going. So I think if you understand this, you know how to run EM. Questions? Everyone is overwhelmed. Okay, but again, I think that the homework will force you to understand this. Admittedly, when we try to write this formally, as I showed last time, sometimes the math gets a little bit too complicated. But really, conceptually, the algorithm is simple. Just writing it down formally is a little bit harder. Okay, so if there are no questions, let's move on to what I really wanted to talk about today, which is driven, I'm just going to show this again, is driven by this comment here, this yellow comment, that makes a distinction between knowing everything about the probability distribution versus just having a model for one of the variables. Call it x0, call it y, I don't care, just that. Okay, so you can still ask questions if you want, but if not, I'm moving to this. Just a reminder, I've been saying this many times, exam. Another comment on homework. So I'm going to give you the statistics of the homework 2 and 3 next lecture. But basically, all the homeworks are very, very good. But we are always missing a few homework. So I don't know if some of you just decided not to do it, or there was some technical problems and we didn't observe that you actually did it. If you don't have a grade, as quickly as possible, tell us that you don't have a grade. Or you can tell us I didn't submit it. It will simplify our life also. But definitely do it as soon as possible. In all the problem sets, we have between 4 and 10 people that didn't submit. And we don't always know, because some of you wake up late and say, oh, I submitted it this way and that way and so on. Check where you are and ask. Okay. Projects, I already said this. Most of you already talked to me about the project. Most of you are doing really exciting projects, so I'm really looking forward to it. Most of you have already made progress in the projects. If you haven't talked to me yet about your project, you're behind. So come quickly, because you just have a couple more weeks, or 4 more weeks or something like that. Okay. So you all know this. This is just a reminder that you have to know this for what we've done, and definitely for what I'm going to do today. So I want to talk about another step in probabilistic representations. So far we talked about Bayesian learning, we talked about naive Bayes, we talked about EM, and today I want to talk about how to represent an arbitrary probability distribution and how to deal with it. How to do inference with it, which means make decisions, and how to learn these representations. So one way you can think about this is we are talking now about unsupervised learning. So you have data. It's the same n+1 tuple that I had before. There is really no notion of a class variable or a label. It's just data. And after seeing this data, you want to say something about this data. You want to be able to make some predictions. You want to look at specific events. What is the probability that x1 is 0 and x2 is 1 and x7 is 0, given all the data that I've seen? So really what you want is to learn the most likely model that generated the data. Sometimes this is called density estimation. The bottom line, just to make sure that I'm saying it at least one explicitly, is that you cannot do this without making assumptions. You already know that, or you should know that. And the question for us is going to be what kind of assumptions it makes sense to make, and what are the consequences? How do we deal with it given that we've made this assumption? Okay, so we already solved this problem to some extent for this probability distribution. What is this probability distribution? This is another way to think about naive Bayes. You've seen this graph now earlier today. This is the assumption that the probability distribution is generated this way. I'm generating y. This, you can think about it as a coin, or you can think about it as the label of the data sets, the 20 news groups that I've given you. Once I have the label, I'm generating, say, the words in the document or the features, and I'm generating the first one with a probability P of x1 given y, the second P of x2 given y, and so on. So the way I generated the data hides this conditional independence assumption, right? I told you I'm generating x1 given y, then I'm generating x2 given y, independent of anything else, and so on. So I'm making this assumption, which is conditionally independence, and given this, we know everything. That's really naive Bayes. The question that we want to ask today, can I relax these very strong assumptions and learn more expressive representation of probability distribution? So for naive Bayes, what we showed is that P of the joint probability, P of y and all the x's, can be written as P of y times the product of P of xi given y. You know this. For example, if I want to compute now P of x1 being 0 x2 being 0, y being 1. I'm being very explicit here, right? We typically don't write it this way. We just say p of x1, p of x1, comma x2, xy. How do I compute this? I marginalize, right? I'm saying, okay, I know the probability of the joint. It's written here. So I'm going to write here the probability of the joint. I'm going to fix y being 1, x2 being 0, x1 being 0. It's written here. And the rest are going to be whatever they can be. And I'm going to sum over all possibilities. That's marginalization. Now, this is going to cost me this computation, right? Because if I have n plus 1 variables and I fix 3, I'm left with n minus 2 variables, which means 2 to the n minus 2 elements in this sum. Hard to do, but in this specific case, it's actually very, very easy because I can do it a lot more efficiently. Just directly from the independence assumption, you know that p of x1, x2, y can be written as p of x1, x2 given y times p of y. Now, this can be written using the independence assumption as p of x1 given y times p of x2 given y, and p of y was copied. That's it. So I don't need to do marginalization. Independence is very powerful, computationally. The reason we make independence assumption is so that we can do these kind of things, so that we can compute things efficiently without marginalizing over large joints. Okay, so now that you know this, you also know that we can compute the probability of any event. Everyone should be comfortable with this. Okay, so now the question is, okay, what about other probability distributions that do not make this strong conditional independence assumption? There are many ways to represent this. So what is a probability distribution? It's a very simple thing. It's a mapping, let's say in this case from 0, 1 to the n, I'm assuming that everything is Boolean, to 0, 1. I can represent it as just numbers. I'm going to write down all the 2 to the n elements in my probability distribution, in my space. And for each one, I'm going to write what is the probability of this element. So I'm going to have 2 to the n numbers, 2 to the n minus 1 independent numbers. That's a representation of probability distribution. Typically, you don't want this representation because it gives you nothing. You'll never observe everything. And if you observe 3 elements from this, you know nothing about the others. You really want to make assumptions. So when you make assumptions, there are families of representations, again, respecting the fact that it's just a function, just a mapping from the 0, 1 to the n to 0, 1. I can write it as multinomials, essentially polynomials in n variables. And this will be a nice representation of probability distribution, one of my favorite representations because it has some nice property, not the most popular one. What is more popular is Bayes nets, which really is representing probability distribution as directed acyclic graphs, and Markov networks, which is very similar but undirected graphs. So given that we cannot do everything, we're going to talk today about Bayes nets, which is, again, think about it just as a representation of a probability distribution. Specifically, what is a Bayes net? It's a representation of a joint probability distribution over a given set of variables. We make independence assumption, because if we don't make independence assumption, we have nothing else but to write a complete graph, if you want, or the whole table of 2 to the n values. What are the independence assumptions that we're making here? There are multiple ways of saying it. Here is one. For all variable x, x is independent of its non-descendants given its parents. So I'm defining what I mean here. Z here is a parent of x, and it's also a parent of x2. X is a descendant of y, as you can see. It's directional, right? All the arrows here go down. And under this assumption, it's very easy to see, and we're going to do some computation a little bit later, that the joint probability distribution of all these variables now can be written essentially as the product of each variable given its parents. P of y I took outside because P of y does not have parents, so it's just P of y. That's it. So that's the key thing you want to know about Bayes nets. A little bit more, okay, so by the way, this is a theorem. So you want to take this network, write it down, and convince yourself that this is really what happens given the independence assumption. I'm going to run through a few examples, but you want to understand that this is a theorem. It's not, part of the definition. Another thing that you want to know is that with every arrow here, or with every group of arrows, for example here, here what I need to know is I need to know the probability of x given z1, z2, z, and z3, because these are all the parents, right? This is the element that is written here for x. For x2, who are the parents of x2? They're z and y. So what I need to know here is p of x2 given y and z, which are the parents. These components are called conditional probability tables, CPTs, and they define the probability distribution. Once I know the CPTs, I can write the joint. Yes?
So if all the xi depends on parents of the xi, which is the z's, and all the z's depend on y, then is it just the xi depend only on y?
Yes, they do. Not only on y, but I'm not saying this is the only way I need to write it. But what you will see is that given z, x is actually independent of y, right? If you think about it. Given z, I don't care what y is, because y determines z, but once I know z, I don't care about y in order to determine x, right? And therefore, it's sufficient for me to write p of xi given the parent. So we're going to do some examples, but basically you want to write it down for yourself and convince yourself that you can always write it this way. Okay, so just to recap what we said, Bayesian network is a DAG. Nodes are the random variables. Edges you can think about as causal influences. And each node is associated with a conditional probability, with the conditional probability distribution, the probability of this node given its parents. You can think about it just as a data structure, something that allows us to write a joint probability distribution. You can think about it as a set of conditional independence assumptions that dictate what is the distribution, summarizes all the assumptions that we had. Either way, you get a Bayes net. Question?
What kind of data structures are usually used to represent DAGs? Are they like trees or?
So it's DAG, it's not a tree. So I think the jury is still out here. I mean, there are many, many implementations of how to do it. I'm going to say one thing about data structure and implementation a little bit later, but I don't know that there is a convention. There are several packages that you can look at and see what they do. Okay, so let's run through an example of a Bayes net. It's a famous example from all the textbooks are using the same one, the burglar alarm example. So this is the story behind it. There's a burglar alarm. It rings if there is a burglary or an earthquake. An earthquake will be reported on the radio. If the alarms rings, on your neighbors are going to hear it and probably will call you. Okay, so what are the random variables that we're going to invent here? We're going to invent these, 6 random variables. Earthquake, burglary, radio, each one is a Boolean. Is there an alarm or not? Was it said on the radio, yes or not? Did Mary call, yes or not? So now I want to include my assumptions. Now, in principle, if I have 6 variables and I want to write the joint probability distribution, that is, I'm going to allow everything to happen, I'm going to have a lot of parameters. Think about it already. I'm going to ask you in a second. But I'm going to incorporate assumptions. These are the assumptions I'm going to make. I'm going to say that if your neighbors hear the alarm, they will call you. If an alarm can ring because either a burglary or an earthquake, and so on. So these are my assumptions. I encoded my assumptions into these edges, and by doing that, I defined a probability distribution. I define independence assumptions that define the joint. Specifically, now you can ask how many parameters do we have in this probability distribution, and you can compare it with how many would we have if we did not have this did not make this assumption. So let's start with the second question. How many parameters would you need without these assumptions? Six variables. How many parameters? 2 to the 6, right? So really I have 2 to the 6 tuples, and each one of them would have a probability. So it's really 2 to the 6 minus 1 because these probabilities have to sum to 1. Okay? So if I would write this in a table, I would need 2 to the 6 minus 1. Yes?
Well, if you don't have those assumptions, then doesn't that mean that they're all independent? So why would you need 2 to the 6 for any?
Okay, so no, when I don't make assumption, I mean everything is allowed.
Oh, everything.
Yeah. So this is, what you're saying is another assumption that is stronger than mine. You're saying these 6 are independent. All I need is 6 parameters. Yeah, but that's a very strong assumption. So when I mean no assumptions, what I mean everything is allowed, and therefore I need 2 to the 6 minus 1 parameters. Now, what are the parameters that I need given this? This is a convention. So the convention is that these arrows encode an independent assumption, and therefore all I need are these conditional probability distribution. Because I drew an arrow from alarm or from burglary and earthquake to alarm, I need to know P of A given E and B. How many numbers are here? Everything is Boolean. Probability of A being 1 given the 4 values of E and B, 0, 0, 0, 1, 1, 0, 1, 1, and the probability of A being 0 given these 4 values. So it's 8 numbers. Really, there are 3 plus 3, because in each case they sum to 1. Because I drew this arrow, I need to know P of J given A, John given alarm, 2 numbers. Really 4 numbers, P of J being 1 given A0 and 1, and P of J given 0 given A0 and 1. But again, every pair sums to 1, and so on. So now you can think about it this way. So let's count all the number of parameters. So I'm going to have 2 here. Burglary does not have a parent, so it's either there was the probability of B being 0 or probability of B being 1. So it's 2 plus 2 plus 8. I already have 12. Here I have 4, 16, 20, 24. So 24 instead of 2 to the 6, which is 64. I already saved quite a bit. Okay, so with these probabilities, which again, this is a convention. The convention is that when I draw the graph this way, I made independent assumptions such that only these conditional probabilities matter, and now I can write the joint. So let's see, how do I write the joint? And this is really, you have to understand this. You've seen this many times. So there are multiple ways of doing it. I want to write the joint. So P over these 6 variables. Here is one way to do it. I'm going to say that this is P of E given P of B, P of the rest given E. I just copied P of E, and now I'm going to break B out. So it's P of B given P of this and the rest given EB. So I copied P of E and P of B here. And now, what am I doing here? I'm taking R out. So it's P of R given E and B times everything. What did I do here? Yeah, plus the, okay, so R is independent. Where is R here? Of A, M, and J given E and B. So I can decompose it this way. And then I need to continue. So here, for example, I copied P of E and P and B. Here, P of R given EB, if you look at R is independent of B given E. You see, R is independent of anything else, in fact, given E. So I can write here P of R given EB as P of R given E. And I can continue this way. At the end, what you see here is what I said originally, which what I have is the product of P of xi given its parents. For E, B, I don't have parents. And here I just write for each variable the probability given its parents. So this is the product of all the information that I have in my conditional probability distribution. Okay, so what do we know? So this seems very simple. In practice, we want to solve two problems. We want to solve the problem of how to learn the structure of the BaseNet. You tell me the variables. In the example I gave you also the structure. But in real life, maybe what you see is data, and you want to know, okay, so what is the structure? How do we learn the structure? That's question one. We're going to do an example of it next time, but the question for you is, what is the guiding principle of learning the structure? How would you decide that one structure is better than the other? There's one code word that we're using throughout this last couple of weeks. Likelihood, right? So you want to maximize the likelihood of a structure. So if I give you a structure, for example here, I gave you a structure. If I gave you data, you can compute the probability of the data given this structure, right? If I give you another structure, say I'm adding another edge from earthquake to Mary, you can compute the probability of the data given this structure, right? This is what I did here. I computed the probability of the data given the structure, right? So now when I give you data, you can compute the probability of E being 1, B being 1, A being 1, R being 0, and so on, given the data. I give you a lot of data, you can compute it given a lot of data. And if I give you two structures, you can compute the likelihood of each one given the data I've given you. And your goal is going to be to maximize this. Now, it seems like a tedious process, which it is, but under some case, in some cases, it can be more elegant and efficient, which we're going to do next time. But this is the important thing for you to understand here is that it's a problem. Given data, you want to learn the structure. Two, you want to learn the parameters of the structure. What are the conditional probabilities, conditional probability table given the structure? Now, these problems are hard. Once you have this, you want to solve the inference problem. That is, you want to know, given an event, and maybe an observation, an assignment, an observation here is an assignment to some of the variable. For example, you know that there was alarm, and you know that John called. What's the probability that there was an earthquake? That could be, or you know that there was alarm and you know that Mary called. What's the probability that there was a burglar? These are the type of queries you want to be able to answer. It turns out that answering these questions is hard. It's very hard. From a computational complexity perspective, this is what is called Sharpe complete. It's harder than NP complete, which you probably heard about. And this is one type of question that you want to answer. It's called computing the probability of an event. You can also talk about another type of inference, which is most likely explanation. So you're given an assignment of some of the variables, and you want to know what is the most likely assignment to the other variables. It's a different question. I don't want to know the probability of a specific event. I want to find the most likely assignment to this set of variables. It's an easier question. It's still NP complete in the worst case. So these are the questions that we want to be able to answer. You want to answer them for two reasons. One, because you want to know, given a representation of the world encoded in this probability distribution, you want to know, okay, so what do I know about this? How do I answer different queries about this world? Two, as we will see, in order to learn the representation, you should be able to answer these questions. This is going to be an intermediate step in our learning procedure. Okay, so how do we do this? So inference that, as I said, is intractable in the worst case, has in general two broad approaches. One of them is exact inference. It's hard, but can be done. I'm going to give a quick example of something that is called variable elimination, just to give an idea of what is inference, and could be approximate inference. And I'm going to give an idea of what is approximate inference using an approach called GIMP sampling. But we're not going to deal with the general case. Instead, I'm going to move next time to talk about a very special case that is tree-dependent distribution. So this is more than naive Bayes. You see that if I would cut T, X, and V here, you will have naive Bayes. So this is a tree, so it's more expressive than naive Bayes, but still it's a tree, so it's a restricted form of probability distribution. I can still write the joint this way, right? So the joint is P of Y times the product of P of Xi given the parents, only that in this case, every node, because it's a tree, has only a single parent. So less parameters. Really, the number of parameters here is linear in the number of nodes, right? So see what we did. We started with the general probability distribution as exponentially many parameters in the number of nodes, right? We had 6 variables, 2 to the 6 parameters. Here we are moving to something that is still better than naive Bayes, but is linear. So it's a compact representation of distribution. And what will be interesting about this representation is that we'll see that we can actually learn it very efficiently. There's a very nice algorithm. This is why I chose to do it. It's a very nice algorithm that allows us to learn more general representation of distribution. So that's what we're going to do next time, and talk a little bit about the general scheme of exact and approximate inference. Questions? Okay? See you Thursday then. How are you? I didn't fix it yet. No. It's. Are you doing the recitation today?
Today at 6, so.
I'll try to do it before that. So let me just get rid of this. So what slides are you using? Do you remember?
Is this the one on the PDF one on the website? Recitation number 9?
Yeah. So it's the naive Bayes with.
Multinomial and normal. Normal.
I'll send it to you in the next hour and a half.
Yeah, no worries. They're like very small things. They're just like there's no the map symbols are all gone or something.
I know. Someone showed it to me last time. So for me, it looks perfect.
Right. No, I understand. Wait, Professor, did you prove the results for Sharpie hardness of?
Yeah.
Oh, wow. Okay. Was it by reducing count to reset?
Yeah.
Okay. Cool.
This was part of my thesis.
Nice.
Yeah.
Hi, Professor.
Hi.
For the first example, you gave the x0 to xn example, the predict x0 example. So we have the hidden variable z, right? And then we're saying that if z can take multiple possible values, and then we give different distribution to generate x0 to xn. And then I'm still not understanding why, let's say, there are multiple possible values for z, and then, let's say if z is a binary variable, and then why is the x0 is a linear combination of the other variables?
You have to work it out. I mean, it's not clear to us.
Okay.
You have to try to write down p of x0 given x1 up to xn, and under the independence assumption, you will get that it's a linear function.
But that's still about the probability, right? But then why is x0 definitely a linear combination of
Oh, no, I'm not saying that x0 is. I'm saying the probability of x0 being 1 is a linear function.
Okay.
So it's basically, all I'm saying is that the prediction is, the prediction task is a linear prediction task. No,
Okay.
not the value of x0.
Okay, then my question is, I'm not saying about the probability. I'm saying that whether the data points in the space is whether linear separable, is that related to how many possible values we can take for z?
Yeah. So if z can take two values, and you generate the data the way I described, first get z. Once you have a value of z, you have a set of probabilities for x1, for x2, up to xn. If you have the second value for z, given that you have a set of different probabilities for x1 up to xn, if you generate the data this way, it's going to be linearly separate.
Then if they can take multiple values, will that be saying that x0 is not a linear separable for all the data points?
Yes, it will not be.
Okay. But can you give me some hints, like how can I derive this conclusion from the probability? Because, I can really...
So go back to what we did for naive Bayes in the class, where I showed that when you learn something with naive Bayes, we called it y then, rather than x0, the probability of y being 1 can be written as a linear function of the x values with some coefficients that are probability of xi given y.
Oh.
It's really the same exercise.
Okay. Yes, so
Basically what I'm saying, the predictor that we get here is a linear predictor.
Okay, I see.
And if x0 takes multiple values, no longer the case.
Okay, I'll try it out.
Yeah.
Thank you.
Okay, sure.
Thank you.
Hi.
I guess I can think of office hours too, but is hook 3 completely graded? I saw Piazza.
No. The problem was that we didn't unmute it. And when some of the TAs started to give the grades, people saw it and were alarmed because they got small numbers, because only one of the problems. But we muted it now, so you won't see it. It will be graded. The plan is by tomorrow.
Oh, okay, all of it.
That's the plan.
Okay. For week 2, I only submitted my code. I didn't really have time to do too much else, and it's not a complete code. But then I emailed it to Andy, and then Andy didn't respond for a long time, and then he was saying like, oh, it was late or whatever, and so then now it's just like a 0, when like originally there could have been some partial credit, I think.
So send me email and Andy. I have a list of people that we think we did not get anything from. I don't know. What's your name?
Lucy, L-U-C-I, and last name Y-I-N.
Okay, maybe I can just check. Here,
Oh, I didn't know they liked the board symbol.
let's see if I can quickly find it. yeah, you are listed among the people that we don't have a grade for.
Right, so I emailed Andy.
When did you email him?
I emailed him that week when the homework was due, and I think there was like, I guess I didn't realize, but there was like a 24-hour rule set because it was before the
Cool.
midterms.
Cool.
I think I submitted it like 36 hours after the due date,
Oh, okay.
and
So
I
I think
emailed it
that
to
was the
Andy.
reason.
And then,
So because yeah, because there was a 24 hours rule. Either way, send me email just that
Okay.
will cover you, and we'll see. But that probably explains it. He did not respond to you?
he didn't, so like, we had a back and forth where he's like, oh, like, this was 36 hours after, and I was like, oh, emailing him back and forth, and he's like, oh yeah, do this. Like, I couldn't email it to him, Gmail wouldn't let me. So then I uploaded it to a Google Drive, and I asked him to download it, and then he didn't respond after that. And then then I followed up, and he's like, oh, well, we can no longer accept it because it's late.
Yeah, I think we will not be able to do it because it's unfair to the other students. Because students.
Or, I don't know, I honestly, I forget when I emailed him.
Okay, so we'll check. So
Yeah.
send me an email. We'll check exactly the time. But if you did submit it after 36 hours, I think we will not take it.
It was just difficult because I couldn't get my, like I couldn't submit it online. And then I tried to email him, Gmail wouldn't let me, so then I uploaded to, like, maybe it would have been on time without all the technical difficulties.
I think
know.
we can allow some small deviation.
It was definitely not more than 2 days, like, it's not even that many points because I didn't complete the homework,
Yeah.
I just,
Okay,
wanted to let
let me
you know.
look at it. Let me look at it, and we'll
Yeah.
see. But so in principle, we allow a small slack. But the issue is that we have 138 students now.
yeah,
If we allow one student, other students, it would be unfair to others because they didn't even think about
right.
being
okay,
late, right?
exactly.
But as I said, let me look at it. If it's a small deviation, then it could be
Okay, okay. And then I wanted to like make a separate appointment with you, but just regarding like my grade in the class, like I don't know, like I think I may be on the border of pass fail, so it's kind of been hard to tell because there haven't been too many grades.
Ideally, do it after Thursday
After
because I'll
Thursday.
have the homework 3
Okay,
then,
okay,
and then I can tell you where you
okay,
are.
okay, that's helpful. Okay.
Okay. Is it a talk?
Sorry?
Is it a talk?
Yes, no. Okay, the untitled lecture.
Hi.
Good to see you. How are you? You just finished class?
Yes,
What are you teaching?
yes.
Machine learning. Finally.
Maybe students.
Good to see you.
Good to see
So
you.
how are you?
Congratulations.
Thank you very much. Fun to be back on campus. Dying of How are you guys doing?
We are doing well. I mean, nobody got the memo. So I just
As busy as ever, yeah.
Yes, it is.
Are you going to like ASHE and things?
And all those things, committees,
I
more.
think I should do name list or something.
If you, yes, that's what I do.
Yeah.
And you volunteer everywhere, which is fun because you have to do things. But I stay socialized.
Yes.
That's,
Keeps you involved, I guess, so.
and when I saw you were being honored, thank you to assist, and I had to come.
I appreciate it. Oh, it's fantastic to see you. Well, it's good. It's
So
really,
we have to get together again.
Yes.
It's been like a couple of years.
Yes.
And,
I think right when you were, right around retirement time was probably when
So
it
it's
started, so. How's
and
George?
retired, and he loves retirement. He loves, because he had a long commute, 50 miles each way.
Oh, yeah.
So now he's like eating chocolate ice cream.
You gotta enjoy your nice house. I mean, you gotta enjoy it. I drive by it all the time and,
So we having again groups, so we'll call it.
yeah, that sounds good.
He's the chef.
Oh,
Although he
yes.
says that he's the sous chef and I'm the boss. working with
Oh, that's,
Christians who's a delight.
she is amazing.
It's amazing.
Yeah,
Trying to raise, and you were going to reach out to you, I want to talk to you. We're trying to create a system of Langer fellows at ACHE, where people are given $100,000, go take a blue sky idea, like Bob did, because
Yeah.
other times he had problems,
yeah.
and try to create new Langers, which is impossible, but that's the thing. So the it will be a big, summer in Cambridge on September 8th, I think, and we want to announce it later.
Are you going, so I think they're doing this big, is that part of his, the Langer kind of reunion?
That's gonna be.
So I'll be there as well.
I might be there.
Yeah. Oh,
I'm
fantastic.
not a Langer family, but I will be there.
He's got a, expands the family, I think.
He's, the more I learn about him, the more it's done.
Yeah.
So just remember, put this up here.
It's like a little locker room in here. Little kitty. And then so normally, there's a table back here. You never know what you're gonna do. But you can sneak back here on the other side, which is useful. It used to be that I come back here and like hand it to people. But I found that to be unnecessary. Like, I'm really not. So, and he has seen this.